Welcome to this walkthrough of Popcorn on HackTheBox. This is number 5 in our series of 10 machines exploited without the use of Metasploit. So we're going to continue using auto recon here. And we'll just let that run to its conclusion. You can pause the video here and we'll return when the results roll in. Alright, and all the results are in. It appears we have SSH and HTTP running on this server at the very least. So it's gone through and done some of the HTTP specific and SSH specific tests through the Nmap scripts. We move into our results for this host and the scans. We have a look at our Nmap results. We can see that port 80 is open. There is a test page running at /test/test.h.php. Appears to be a logon at test as well. And it's identified an icons folder. It's running an Apache 2.2.12 server. And may be vulnerable to a denial of service attack under CVE 2011-3192. Again, that's not going to be particularly useful for us for denial of service, where we're looking for access to the server and subsequent privilege escalation. So the Nmap results show us that HTTP and SSH services are open. We can follow on the GoBuster scan results as well. And it has identified quite a few avenues for us. A great many of these are not accessible to us. They're status 403. We'll stick with the status 200s rather. So we have index.html, index.html again for whatever reason, and these refer simply to the home page for the site. So we can go there. And as we can see, this is just a very simple and generic test page. We can also see that there is a /test endpoint. And it's showing us the results for the PHP configuration page, which should not be left accessible. This lets us know that the back end of this website service is very likely PHP based, and gives us the version if we were interested in a PHP specific vulnerability. So this /test.php page should be removed, and all indications of the backend code type removed wherever possible. There was also supposed to be a /logon page. This doesn't appear to connect us with anything additional, but we can still see all of the information for this PHP service. As you can see, it is quite extensive. The last on our list from GoBuster is a page called Torrent, and this appears to be the homepage for a file sharing torrent host site running Torrent Hoster. So the homepage contains some news items. The browse page shows us that the site is hosting a copy of Kali Linux. If we look into the details of that, we can see that it's been uploaded by someone named admin, presumably the admin for the site. Screenshots are something that can be uploaded along with the torrent files. But accessing that admin information or downloading the file both require us to log in. The upload page also requires a login. Forum page tries to connect off to another part of the internet, MyanmarTorrents.com. The server isn't connected to the internet on its own, so it's not going to resolve. The stats page has information about torrent peers and file stats, more news in the news section, and so on. I did try SQL injection testing on the login, as we'd done previously, but didn't find a vulnerability there. We are, however, permitted to register as a new user. So we can provide a username and a password. Confirm that password. Provide an email and fill in the CAPTCHA. And we can register our user. Username test with the password test. So when we attempt to log in, now if we want to have a look at that file and what else has been uploaded by the same user admin, we do get results. We're also able to access the uploads area. So we can try to upload files. Some experimentation with this shows us that this portion of the upload process is actually reasonably secure. The page only uploads valid torrent files, and it does its check based on the content of the file rather than just the file extension. It even ignores torrent files that are already part of the site. Now we can grab a sample torrent file to test uploading. Grab the Sintel file here. Should be in our downloads file. We can provide an optional name and description. Doesn't really matter at this stage. Call it whatever we want. And when we go to upload the torrent, it uploads successfully. So once we've got the file uploaded, then we're able to upload a screenshot for other users to see what the torrent contains. And this is a more vulnerable area of the site. So if we create a simple PHP-based reverse shell, let's call it upload.php, and we give it a simple PHP reverse shellcode. Just modify our IP address. So this will try to open a connection back to us at 10.10.14.24 on port 9999 and open up a bash shell for us, an interactive bash shell. Save that. And when we go to edit, now we have an update screenshot area. From there we can grab our upload.php and try to submit it. And it tells us that we have an invalid file. If we go back and have a look, that's because the allowed types are JPEG, JPEG with an E, GIF, or PNG. And that's really all it's supposed to allow us to upload. We can see, however, if we change the name of our upload file from .php to upload.png and try to upload that it does allow us to upload it. So it's just checking the extension. So we're able to upload the same file simply with a different name. We can have a look at the location of that. If we refresh the screen, we can see that it has uploaded the file as this long string of characters here, .png. which is the link we see at the bottom. The renaming of the hash of the file is a good step. Although the file name is not fully anonymized, it's actually the SHA-1 hash of the torrent URN. So files uploaded for this torrent will always produce the same file name for this, for the screenshot. And with direct access to it from the torrent details area here, it hardly matters. We have direct access to it. Most importantly though, as we've found, it keeps the original file extension. So it is .png. So the next thing to check is where the file extension check is happening. Is it happening on the server side, or is it just happening on the client side? And for that, we'll need to start up burp. I've got it set up, ready to intercept our traffic. So we'll turn intercept on. Let through that just to load the page, turn it back on. And now we can select our upload.png file, try to submit that, and we've captured that request. If the check was only happening on the client side, it's past that already. It's moved on to the point where it's going to send it to the server, and before it gets to the server, we're going to change the file extension back to PHP. And we're successful, and it's uploaded upload.php. We'll turn our intercept off, close our little window, refresh our page, and as you can see down at the bottom, we're no longer attempting to open a PNG file. It has retained the extension, and it will try to open a PHP file. So we can set up our listener. And as we can see, it's attempting to make a connection. It doesn't quite do it. It drops it right away. That's all right. We can modify our shellcode. We'll just save it as PHP. And just simply select a different PHP-based reverse shell. So this one's a little more involved. Change our IP to 1424. Save it. Move it. Intercept our traffic. Attempt to upload. Modify the PNG to PHP. Which is successfully uploaded. Turn our intercept off again. Reload the page. Restart our listener. And browse to the file. And now you can see we've got a shell. So we can edit our screenshot, we can upload our PNG file, we can edit the file name to upload.php in the intercepted request. It uploads successfully, so only a client-side check is being made of that uploaded file. And it's just doing so by checking the file extension for conformity to the JPEG, GIF, or PNG allowed file type extensions. With our web proxy, we can intercept the upload request after the client-side check is complete, and then alter the file extension before it reaches the server. When the file goes through, it does go through an additional server-side renaming process, but it retains its file extension. And that file is accessible to us in the torrent details area and executed within the context of the PHP-driven web page. So all the client-side checks should only be considered as an efficiency rather than a security check. Client-side checks prevent wasted time and processing of uploads if they have the disallowed file types. But that check should be performed again by the server on these supposedly valid uploads to ensure that they haven't been tampered with en route to the server. The file type check should also look at more than just the file extension to determine if it's an allowed file type. Looking at the expected header and footer bytes, the so-called magic bytes for a file type, and the resulting upload should be held in an area of the server from which PHP code is not configured to run. That's another major issue here. So in this way, we've connected back to our Netcat listener. Our first set of code broke down the connection immediately after giving us shell, but that's fine. We have a different payload, different PHP payload, and that lets us connect properly this time. So we're connected. We can run who am I? And we can see that we're in as the expected www data user, the account running the web server. And we can cat out the user.txt file, which a little searching will tell us is in /home/George. And there we are. But we don't have access to the root folder just yet. We can use a simple server to bring our lin-enum script over to the popcorn machine, as we have in the past. The results there are not terribly helpful. Indeed, what can get us a root shell, we can get from a single command, and that's uname-r, which tells us the Linux kernel version running on this machine. In this case, it's Linux version 2.6.31-14-generic PAE, and that puts me in mind of a dirty cow exploit. So in versions of the Linux kernel between 2.6.22 and 3.9, so our machine is a candidate, there is a race condition in the copy on write, or COW, the cow portion of memory mapping, that allows an attacker to write to otherwise read-only areas of memory. So this is an instability in the way that these versions of the Linux kernel access memory over many thousands of iterations during a copy on write action, allowing an attacker to write to portions of memory that should be read-only. So the particular version of the dirty cow exploit that we're going to use creates a private copy of the etc password file in virtual memory, and then it initiates writing of our malicious content back to disk. In this case, it'll simply be an additional root level user and their hashed password back to the etc password file. Now at the beginning of the write process, the kernel locates the original read-only file in physical memory, but the dirty cow exploit interrupts the rest of what would otherwise be an illegal write process with an order to discard another copy on write private copy in physical memory, which gets created when that writing process is initiated. And as a result, the kernel doesn't know where it's going to be writing to when it gets to that point. So it gets a bit confused, and it writes to the original read-only file instead of returning an error. So this vulnerability has been fully patched in all versions of the Linux kernel since 4.8.3. It's really a simple matter of updating the server's OS to the latest version of the Linux kernel. And there are a variety of dirty cow exploits out there. The one that we're going to use, which adds a root level user to the machine, can be retrieved from the exploit DB. So we'll use searchploit, and the one we're looking for is 40839. So we can transfer that file then to the victim machine using a simple HTTP server in the folder where the 40839-C code is located. So we're serving that up from the local directory. We do have wget accessible to us on this machine. And we're connecting back to 10.10.14.24. And the name of the file we're trying to grab is 40839.c. We can see we've gotten the request for it, and it is saved to our remote machine. The next step will be to compile it locally using GCC, which we also have on this machine. This is the GNU compiler collection. And we do that with some options that are given to us in the code itself. So if we have a look at that quickly, we can see that it is going to be attacking the etc password. It is going to create a backup of that so that we can restore it afterwards. The process, you can see, is going through many millions of times, in point of fact, trying to interrupt that write process in the middle before it's attempted to write to memory where it should not. And if we really wanted to, we could modify the username and the user ID and group ID and so on, their home shell, etc. In this case, it's going to create a user with user ID 0, which is the same as root in the root group with the root home directory. So it gives us some compiling instructions at the beginning. GCC -p thread 40839.c is the name of the file that we've uploaded it as, and we're going to output it as just cow. All right, so it's compiled, and then we simply run our file. We provide it with the new password. Let's say test pass, and we let it run. Now this may take some time. It may return rather quickly. If it does take too long, it is not a bad idea to simply kill the process, which will kill our shell, unfortunately, but that's easy enough to get back into. But we could SSH in, as we know that's available to us, and complete the exploit that way. So I'm going to kill this shell, and we'll attempt to log in as the user Firefart. Not a technical term, simply the name, the moniker of the person who wrote this code. Our first time connecting by SSH to this machine, so we'll accept the fingerprint, provide it test pass password, and a little slow, but we're in. So now if we are to type who am I, we have the user Firefart. As we can see, they are user ID 0, group ID 0. So now we can collect our root flag. If we didn't have SSH available to us, we could still get in to the machine. We'll just reestablish our listener. Click on our image again, which creates our connection. So we're still in as www.data. We would need to su, switch users, to Firefart. And unfortunately from this terminal that we've created, we're unable to do that. We do have access to Python in this machine though, and so we can upgrade our shell with a Python command. So this is importing the Python terminal. It's going to spawn a Python terminal running sh. So now we can switch users, provide our test pass password, and we're in again as Firefart. So that would still allow us to collect our root flag. So having done that, and being good house guests, we'll go through and remove all of the shell and the dirty cow exploit code. So we'll begin by removing our reverse shell, removing our 40839.c code, removing our compiled cow binary, and last but not least, removing our backed up password file to replace the current etc password file, removing the Firefart user. You can see we're no longer added at the bottom here. We just have the original users. So this relies initially on two items. One, that we have this test page indicating to us that we're running PHP on the back end. That and what is a largely unrestricted file uploadability for the screenshot anyways. If the screenshot upload was being as carefully checked as the torrent file upload, this might not be an issue, but we are able to upload an arbitrary file, sneak it past client-side protections, intercept it after those client-side checks, change the file name back to our desired file name, in this case PHP, and execute that code simply by clicking on the screenshot file itself. Once we're inside, we can make use of the fact that this Linux kernel hasn't been updated in quite some time, and it is vulnerable to the copy on write memory vulnerability that allows us to write into areas that should otherwise be read-only. So we're looking at, first, better user data sanitization, as well as the removal of sensitive information being leaked by the system. And in the end, for our escalation, that can be stopped simply by updating the kernel.